Okay, so here's our example problem we're going to work through here. So this figure to the right shows 3 point charges that lie in the xy plane in a vacuum. Find the magnitude and direction of the net electrostatic force on Q1. So to be clear, there's interactions with all of them. All of them are interacting with each other, and they will all end up experiencing forces just because they're near each other. But we only care about what the total force, magnitude, and direction on Q1 is. So it's going to be experiencing a force because it is nearby Q2, and it's also going to be experiencing a force contribution from this Q3 over here. And so our job is to find the net force vector, both magnitude and direction. And so we're going to do so by solidifying what our axis is. So this we can call x, and this we can call y, right? It's x and y direction. And we're just going to sum our forces in the x and the y. We, of course, are going to need to use Coulomb's law, or the electrostatic force, to figure out what those forces actually compute to. So if we're doing the sum of the forces in the x and the sum of the forces in the y, it's going to be equal to something, right? In the end, what we will do, this is just top-level strategy here, to find the total force vector, we're going to find it in the usual way by taking the square root of the sum of the squares. Right? And then we can find the direction that it points relative to the x-axis by taking the inverse tangent, just like we would usually do, right, of, I guess I'll do this. Sum of the forces in the y over sum of the forces in the x, right? So that's generally what we're doing. So now let's find all of those sums of forces. So I'm going to carry it down here. All right, so we have a force that lies completely in the x direction, right? This interaction here, it's going to be completely in the x direction. And because they are attractive, they are opposite signs, they are attractive, so the force vector is going to be something in that direction. We don't know its magnitude yet, but we know it's going to be in that direction for that force, F13, right? It's the force on charge 1 due to charge 3. This other one, it's also going to be attractive, right? So this is F12, but bully, it does not lie in the x direction or the y direction alone. It has components in each of those. So if we zoom in, we can find our component vector. So it lies some amount, F12, in the x direction, and it lies some amount, F12, in the y direction, right? And we, of course, know that this is that angle, 73 degrees, right? And so that means that we have this situation. I'm kind of going through this slightly granularly because it's the first time and you may want to have your memory jogged. Usually we will go through these types of things a little bit quicker, but I'm going to go ahead and go through slowly real quick for the first time. So just zooming out here, we have our F12, or zooming in rather, I guess, and then, oops, F12 also, but in the x direction. So if this angle is 73 degrees, then how can we figure out what each of these components are? Right? Well, this is a right triangle you can consider, right? And so cosine of 73 degrees is going to be equal to adjacent over hypotenuse, hypotenuse being the full F12. And so that means that cosine of 73 degrees is equal to f12 in the x direction, that component vector, divided by f12. And we can rearrange that such that we move this guy over, right? So f12 in the x direction, what we're wanting, is equal to f12, that full red vector, which is the force on charge 1 due to charge 2, right, times cosine of 73 degrees, right? So this is really what we want, right? So we found that component. Likewise, you can go through the same reasoning to find that f12 in the y direction, that component, is going to be f12 times sine of 73 degrees. So this is equal to f12 sine of 73 degrees. All right. So now we have our component vectors. So now we're going to return to our sums of forces. So we have sum of the forces in the x. What contributions do we have just in symbolic form? We have f13, right? And we have a component of f12, right? So plus f12x, so that would be this guy here. So f12 cosine 73 degrees, right? It's just the x component of f12. That's really all we've done. All right, and now we can go ahead and apply our Coulomb's law to figure out what the heck those exactly are, right? So f13, so this will be equal, I'll just keep it all in the same calculation here. So this is going to be k times q1 times q3 divided by r13. They give us this distance here, r13. Plus f12 is going to be a similar thing. So k q1 q2 divided by r12 now. And that one, it's just the component that lies along that direction that we're counting, right? So we have to include this cosine 73 to make sure that we're only capturing the component of that force, F12, that lies in the x direction. All right, so next line, we can expand what that actually is. So you can, I guess, take some things out of it. You can pull the k out of it, but I don't think that that saves very much time, so I will write it out all together here. 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Looks like I miswrote this up here. Yes, this needs a Newton in there for the units. So K has units of Newton meter squared per Coulomb squared. Sorry about that. So I'm working my way here, just writing these points down. So the next one is charge 1, which is 4.0. This is a micro Coulomb. So that's times 10 to the negative 6, times 10 to the negative 6. Look up metric prefixes. You can Google for images, and they have some really slick ones. I have to reference it all the time until you memorize or become familiar with what all the different prefixes are. No shame in Googling it up. All right, and then Q3, the charge of Q3, the absolute value of 5.0 is 5.0 times 10 to the negative 6th Coulomb. Oh my gosh. Divided by R13, which is 0.10 meters, right? And so that takes care of this term. Now we have to do this big term. So I'm going to do a big plus sign down here, and it continues on. So we have another 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. It's going to be the same Q1, 4.0 times 10 to the negative 6 Coulomb. And now we have Q2. So Q2 was negative 6 microcoulombs. So absolute value of that, and converting it to coulombs, is 6.0 times 10 to the negative 6 coulombs. And underneath all of that is R12. So they give us that the distance between Q1 and Q2, R12, is equal to 0.15 meters. It's already in meters, so we don't have to worry. And then the last thing we have to account for is this cosine of 73. Just like we said before, that makes sure we're only capturing the component that lies in the x direction. Alrighty, so if you compute all of that out, make sure that your calculator is in degrees and not radians, since that's what's given, 73 degrees. And you compute all of that out, make sure you get your parentheses correct and everything. Then you should find that that is equal to, where are we at here? You should find that that's equal to 21 newtons. All right, so that is our Fx. I usually put a bar behind quantities that are going to be relevant later, right? We're going to need that because we're going to stick it in to our square root of the sum of the squares of the components of the total vector, right? So we'll keep track of that. So now, sum of the forces in the y, same deal, but this one's a lot easier because there's only one force that lies in the y direction. It's only our component force, F12y, right? I'm looking here. There's only one that points in the y direction, the component of F12 that lies in the y direction. So we have F12 sub y, which we know is F12 times sine of 73 degrees. Yeah? So we'd figured out over here. So we go through this same effort where we say that this must be equal to 8.99 times 10 to the 9th newtons times meters squared per Coulomb squared times charge of 1 is 4.0 times 10 to the negative 6 coulombs times charge of 2 is 6.0 times 10 to the negative 6 coulombs. It's absolute value, that's why we ditched the negative there. Don't forget that. And that's all over the distance between them. Oh, I forgot to add the little squared on this, so this should be squared. There, because Coulomb's law has the distance between them squared. Apologies. Squared. All right, so the distance between them squared, so that's 0.15 meters squared. And the last thing is that sine of 73 degrees. So if you calculate that out, making sure to include the square that I forgot to write down before for our sum of the forces in the x, you should find that you get 9.2 newtons. All right, so now between these two, we have everything that we need to find the total force vector, right? So what's happened here is, let me use a completely brand new color that might show up, green. So what's happened here is between these two red forces, there's going to be some total force, right? That's like something in that ish direction, and it's going to have some ish direction magnitude like that. Who knows? Probably going to be, I guess it's just, you know, the red ones aren't drawn to scale, so the green one isn't either. But it's going to look like that. And so what we found is the x component of this green one and the y component of this green one, right? And so we have both components, so then this we can find by taking the square root of the sum of the squares. We can find F total, right? It's the total force on charge 1. So if we take, so F total can be found by taking the square root of the sum of the squares. So sum of fx squared plus sum of fy squared. And so that's equal to 21 newtons squared plus 9.2 newtons squared. And if you compute that, you get a magnitude of 23 newtons. That one we can box in because that was one of the answers it was requesting. The other task that we had was to find the angle. So the angle, which I've just referred to as theta there, the angle is back in green here, not this 73 degrees. That's giving the angle of the line between Q1 and Q2 with respect to the x-axis. This theta that we're going to find is the degrees respective to the x-axis that the F total vector lies in, right? That we've kind of depicted in a lighter green up there. And that is found, again, with both components. So that's found with the inverse tangent of the y over the x. So sum of fy over sum of fx. And if you compute that, then you should find that theta is equal to 24 degrees. So that is the direction. So let's see, 24 degrees, did I get it about right? Is this angle here, is that about 24 degrees? Not too far off, I would say. Maybe I'm a little high. Mine looks a little bit more like 45. All right, so we went through that a little bit more granularly than I think that you will need to on your own. If that was too fast-paced, you'll just have to do more practice problems to familiarize yourself with vector components and vector addition and all this kinds of stuff. If that was painstakingly slow, well, you're in good shape, and we're past it. Alrighty. So next, we'll talk about the electric field.